Okay, we are given we we are now going to prove a theorem which goes like this. Okay, we have a function f from k to h. Okay, whereas h is a Hilbert space and k is a subset of h, and it's not just any subset. K is closed and convex both. Okay, K is closed and convex, and we have what we have that there exists X belongs to K interior such that we have this inequality is satisfied. What is this inequality? Is like this: fx comma y minus x is greater than or equal to 0 for all y belongs to K. This is called variational inequality. So basically what we have a solution of variational inequality in the interior of K. Okay, then if all this hypothesis follows, then we have fx is equal to 0. Okay, this is the theorem. We need to show that fx is equal to 0. Okay, now how we are going to prove this? Let's see. Okay, how our aim is to show that fx is equal to 0. This is equivalent to show that fx norm is equal to 0. Okay, fx norm is equal to 0. There is no doubt. I don't think there is any doubt in that. Fx norm is equal to 0, and which is same as if I show fx norm square is equal to 0. And what is use of the square is that we can have fx comma fx is equal to 0. So we will show this. If we can show this, then it will implies this, which will implies this, and then this. We will get fx is equal to 0. That was our aim to show. Alright. Okay, so we have changed our problem to the fact we only need to show now that fx comma fx is equal to 0. Okay, we are given that fx comma y minus x is greater than or equal to 0 for all y belongs to K. Not only that, we are also given that x belongs to K interior. So there exists a ball. I think this is a ball whose radius is epsilon and center at x, which is a subset of K. Yeah, there exists a ball. We can find an epsilon small enough. Okay, so I will write the ball just to make it more clear. Those z belongs to H such that z minus x norm is less than epsilon. Okay, now we want to use these two facts. Okay, we have this first fact and we have the second fact to show this. Okay, we have this. We will choose y very smart enough to get here. Okay, how are we gonna do this? Okay, so if you see this, I will make it from red so that it's easily visible. Okay, if we see this, we need to get from here to here. Okay, we can see that we have for all y belongs to K, we can choose y smartly to get here. What is the most smart choice we can have? We can take y is equal to like x minus fx. Yeah, that's a natural choice, because if we put I will make it, wait a second, if we put this y is equal to x minus fx in this one, then x will get cancelled, we get somehow fx, some kind of thing can happen. But the problem is that we can choose y belongs to k. We cannot choose like this. We have to somehow make it so that it belongs to k. And now we will use this, that we will use the second fact now. Now we will use the second fact here in choosing y. Okay, let's see how we choose this. Okay, what if I choose my y to be x minus fx by fx norm into epsilon by 2. Why does I choose like this? First of all, I will show that y belongs to bex. I don't think it's so difficult to prove. Simply check y minus x norm. This will give you epsilon by 2, which is less than, I think it will, I will left it as exercise to show this. It's a very simple computation. Okay, so y belongs to bx, which is a subset of k. So now our y is in k, and we can use this in this inequality here. Sorry, we can use this in this inequality here. Alright, now I will change my color. Okay, now we will show this fx comma y. We will put the value of y, which is x minus fx by fx norm into epsilon by 2 is greater than equal to 0. From this condition, I can name it, no, they don't write. Okay, from this condition, x minus x2 is also there. This x will get cancelled, and we get fx comma minus fx by fx norm into epsilon by 2 is greater than equal to 0. Up to now, we have proved that fx comma minus fx by fx norm into epsilon by 2 is greater than equal to 0. Okay, we can take out, okay, these are all real numbers here. We can take them out in inner product. We are in a real inner product, no problem in that. Even we can take out this negative 2. So we get minus epsilon by 2 fx norm fx comma fx is greater than equal to 0. Okay, these are always greater than 0, all these terms. So this means that then we must have minus fx comma fx should be greater than equal to 0. This implies that fx comma fx is negative. This implies that fx norm square is negative, but we know that fx norm is always positive. This is possible if and only if we have fx is equal to 0. And we are done with the proof.